Alright guys, we're going to keep moving along with the third part of our polynomial notes videos, and we're basically getting into, the different things that we might see, how that function might look, and then how we want to graph that function. So first things first, we have a fourth degree polynomial. We're going to compare to the parent function 4x to the fourth. We're going to need to find our x-intercepts. That's going to be a little bit difficult now. We have an x to the fourth power here. We have, 5 terms. There is nothing that we know that we've been taught through Algebra 1, Algebra 2, and pre-calculus that would tell us how to get the factors of something that's a fourth degree polynomial with 5 terms. We don't have strategies for that. This doesn't fit into grouping. It doesn't fit into sum or difference of cubes, difference of squares, factoring a trinomial. There's no GCF to pull out. So for that reason, you'll see that in certain ones, we allow you to do things on your calculator. So we want you to put this into your calculator. Okay, and for the most part, the one thing that we're really going to want to see on the calculator is the zeros, okay, the x-intercepts, okay. Now, let's talk first about how many we should find, okay, because it's going to get us into our first little talk about imaginary zeros here. So we're going to take a few notes here down at the bottom, okay. A degree D polynomial should have D zeros, a combination of real and imaginary zeros. Okay. Now we need to, taking into account multiplicity. Okay, so like x to the third power, just f of x equals x to the third. The only zero there is 0 because it's to the third power. There's basically 3 of them. Or if we wrote f of x equals x plus 1 to the third. Okay, this is a degree 3 polynomial, but it does not have 3 zeros. It has 1 0 3 times, that 0 being negative 1. Okay, so we need to make sure we take into account that multiplicity. The other thing we need to know is that imaginary zeros come in pairs. Okay, we'll talk about that when we get to it, and then there's a box for us to write down some things later in the notes. It's called the complex conjugate theorem. Okay, basically if something is an imaginary zero, its conjugate is as well. Okay, well, first things first, why don't we plug this into our calculator? Okay, x to the fourth minus 3x to the third minus 5x squared plus 29x minus 30. You can pause the video, plug it in, and then play the video. So after plugging it in, you should see that we have x-intercepts, or zeros, real zeros, these are the real ones, real zeros, of negative 3 comma 0 and 2 comma 0. 1, 2, 3, 1, 2. So we've got negative 3, we've got 2. Notice that from your calculator, you notice that they cross. So these will both have an odd multiplicity. Okay. Let's see here. The y-intercept, negative 30. Pretty easy to see if I plug in a 0 here for all these x's. Down here, we'll just call that negative 30. Okay. All right. Domain, negative infinity to infinity. Range, well, it's going to be a fourth degree function where the end behavior is up and up. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y still goes to infinity. That's the up and the up part. Okay, so we should be able to get a decent sketch of this. Okay, using your calculator, you should be able to find the vertex of this fourth degree polynomial. The y value is negative 70.66. So we come down here to negative 70.66. We just used our calculator. Then we're going to sketch the graph. It's based on kind of what the graph looks like So we got negative 3, we got 2, we got negative 30, we got negative 70.66. Then we sketch the graph. So the range then, negative 70.66 to infinity. Sorry, that should be a bracket. How low and high the graph goes. From negative 70.66 all the way up to infinity. Those are our possible y values. Now the imaginary zeros here, okay? So if we tell you, or let's say we give you information that shows you that some x value is a 0, or we allow you to use the calculator to find that there are real zeros. So we now know that we have a real 0 of negative 3, we have a real 0 of positive 2, okay? Back in Algebra 2 Trig, you guys learned a skill to be able to help you factor that if you divide, and in this case we'll use synthetic division, by the factor that creates a 0, there's going to be a 0 in the remainder. Okay? So what we're going to do is we're going to divide by the real zeros. And in this case, we have 2 real zeros. Okay? So we're going to divide by the first one. We're going to get a result. Then we're going to divide by the second one. We're going to get a result that hopefully we can work with to figure out the other imaginary zeros. And by hopefully we can work with, you have to be able to work with them for us to ask you this question. Okay? And in this case, we're going to use synthetic division. Okay? So either you're using synthetic division with the values of negative 3 and 2, or you're using polynomial long division with the factors x plus 3 and x minus 2. Okay? Alright, so let's remind ourselves how to synthetic divide. I put that 0 in the box. I write out my coefficients of the polynomial. 1, negative 3, negative 5, 29, and negative 30. 1, negative 3, negative 5, 29, and negative 30. Okay, I bring down the first term. And remember, we just multiply and add. It's a series. Multiply, place that here. Add. 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 Now, if negative 3 is a 0, we should not have a remainder. Okay, that's good. A, we found the proper 0. B, we don't have a remainder, so we know we're doing this division properly. Okay, we said we had 2 zeros. So I'm going to divide by the x minus 2 as well. I'm going to put a 2 in the box. And we're going to divide, multiply, add, multiply, add, multiply, add. Are we happy with what came out? There was no 0, or there was no remainder again. Makes sense since these are both zeros of our function. Okay? So what that means is the factored form of this function. Okay? That's what we just did. We found the factored form. Okay? One of the factors should be x plus 3. How do we know that? Negative 3 was a 0. Another one of the factors should be x minus 2. How do we know that? Positive 2 was a 0. Okay? And then the last factor will come from the result of our synthetic division. In this case, x squared minus 4x plus 5. Now, why aren't we factoring that any further? Well, we can check to see if it's factorable, but you should pretty much know going in that what's going to result is not factorable because it's going to help us find our imaginary zeros. If this was factorable, then we would have 2 more real zeros, and we wouldn't need this whole thing. Okay? Now, if it's not factorable, how in the world are we going to figure out the real zeros, or the imaginary zeros? We're going to use the quadratic formula. If I want to see what zeros come from this factor, well, set it equal to 0. Okay, I did that. I can't factor it. I have to use the quadratic formula. X equals negative b, negative negative 4, plus or minus square root b squared minus 4ac all over 2a. Okay. How do I know this is going to be imaginary? What's going to happen under the root is going to give me a negative. 4 plus or minus the square root. Negative 4 squared is 16. Minus 20 gives me a negative 4 all over 2. The square root of negative 4 is 2i all over 2. I simplify each one of these, and my final answer, 2 plus or minus I. Those are the 2 imaginary zeros. 2 plus I and 2 minus I. All right. How many zeros in total did we have? Well, it was a fourth degree polynomial. Okay. We notice that the zeros cross, multiplicity of 1. We got these two factors from knowing that the 0 is -3 and 2 in the calculator. We use synthetic division to basically factor this, write it in its factored form, and we had something to work with here. It factored down to a quadratic that we could work with. We found the other two zeros. How many zeros total? 4 zeros for a fourth degree polynomial. In this case, there were 2 real zeros, each with a multiplicity of 1, and 2 imaginary zeros. All right, let's turn the page and go to example 6. All right. Without a calculator, sketch the graph of the function. We should be able to sketch this. It's already in its factored form. Parent function. We have a 6th degree polynomial. Okay. The x-intercepts. We have -2. We have 1, and that has a multiplicity of 2. And we have 3, and that has a multiplicity of 2. What that means is at 1 and at 3, this polynomial function will bounce. Y-intercept, let's plug in zeros everywhere. 0 plus 2, 0 minus 1 squared, 0 minus 3 squared. Let's do some math. -4 times 2 times 1 times 9. Last time I checked, that would be -72. All right. I think I skipped over a problem in the notes. We have these notes a little bit misnumbered here. So let me actually go back, and this should be the page that we're working on right now. So what we'll do is we'll finish up that example on the next thing of notes, but we're going to, or the next part 4. We'll talk about the conjugate zeros theorem really quick, which we just did. We're going to put some notes here in the box. It says if the polynomial P has real coefficients and the complex number z equals a plus bi is a 0, then a minus bi, its conjugate, is a 0 of P as well. Basically just wraps up what we talked about on the last page. Now, what we did was we saw using the quadratic formula, and in the quadratic formula there's already a plus or minus. So that doesn't necessarily allow us to generalize that there will always be real zeros that come in pairs, but there are. So for example, if we tell you that 3 plus 2i is a 0 of P, then 3 minus 2i must be a 0 of P as well. Okay? So anytime there is one complex 0, now complex is another word for an imaginary number. Okay. All right. So I know, like I said, we kind of went a little bit out of order here. So we'll attack example 6 and 7 when we get back to part 4 of the